In this video I'm going to show my Sinclair ZX Spectrum emulator, which is written just in C programming language, and I'll show it just writing a basic program, and then I'll demonstrate it playing a couple of games, and then I'll go through the source code and explain how it actually works through the C source code. And in the last couple of videos I actually showed a Sinclair Z80 emulator using ANSI C and a Sinclair Z81 emulator using ANSI C, and it's surprising how very similar even the Sinclair ZX Spectrum emulation is to the first two emulators. Even though it's a colour computer and it's got beepy sound, actually the source code itself is virtually the same as the previous two emulators. So I'll write a quick demonstration program just to demonstrate basic programming on it. The actual keystrokes are on the key tops of the keys, so I'll do my best to remember which keys actually to press. And I'll just print out the characters from 32 to 255. So in the ZX80 and ZX81 they had custom character sets, whereas the ZX Spectrum they actually moved the ASCII character set. So it's using ASCII character codes. So that simple program should print out the character set. So it runs as the actual Spectrum would run. So next I'll demonstrate a couple of games running on the machine, but I'll use it using a power capture device rather than, at the minute I'm using the virtual machine and then capturing the screen through there, but the virtual machine capturing information takes up a lot of CPU time, so it actually slows the machine down a bit. So if I use the power capture device, even though it's low quality, it will show the games running in the proper speed. So it boots up, and I've got a menu if I hit the escape key, which allows me to load a snapshot. So I've downloaded some snapshots, and one of my favourite games of the past is Jetpack. So it loads straight up, and they load quickly when they're loaded like this. And I'll just play the game a little bit. So the display quality, because it's capturing through the power device, it's going to be, well, it's going to be like an old TV actually. It's probably more realistic to how it used to be, but it plays well. And let me just turn up the volume a bit. I've got it coming through an amplifier. And I've implemented some sound, but it probably needs a bit more work on the sound side of things. But the rest of the computer runs okay. Seems to emulate it quite well. I used to play this game and go from level to level to level and not die at all. But I'm not as good as I used to be. So you're one of my favourite games of the past. The games writers used to really be good at coming up with some really neat ideas for games. These are really addictive games. I'll load another game just to demonstrate another game. So this is Sable Wolf. Again, I've lost, not as in practice as I used to be at these games. Oh, well, that wasn't very good. So like I was saying earlier, the actual emulation of the Sinclair Spectrum is unusually very similar to the emulation of the ZX80. There's not much difference at all. So this file here is a Z80 CPU emulation. Now that's going to be the same across all of the machines because all the machines have a Z80, and the Z80 just performs exactly the same tasks whatever machine you're running. So in here I've got about 500 opcodes, so I won't scroll through them all because it would take probably a couple of hours to go through all of the opcodes, but they're all basically of this kind of form. So you've got the opcode ID, which is the machine code number for that opcode. This is just a debug string, which is just there to create debugging information so I can understand what's happening, but it doesn't get compiled in the actual release code. And then you've got the actual opcode operation itself, which is usually just moving something from one piece of memory to another. So you can see there's more complicated opcodes here for doing subtraction, and it just moves things around memory and just performs operations on those bits of memory. And the actual Z80 isn't much more complicated than that. If I go through the include file, which I haven't done before for the Z80, I've got in here some functions. Now these functions up the top, this load ROM is just about loading stuff into memory. So these are kind of helper functions that aren't really to do with the actual Z80 operation itself, but I've put them in the Z80 emulator because the Z80 source code, because no matter what machine you're going to be emulating, these functions are going to be relevant to that. So I've got some specific stuff in here as well for loading and saving particular files into memory, because the memory itself I've put in the Z80 CPU code as well, because the memory is just an array of bytes, so it doesn't matter if I just sling it in the Z80 stuff and really make this into almost a microcontroller itself, and then I do all the memory management in here, because every computer needs memory, and I just supply the full 64K, which is the maximum that the Z80 can actually address. Then every machine that I have can have up to 64K, but actually the amount of memory I've provided is more like 128K, but actually I've provided a bit more than that, because the Sinclair Spectrum 128 and +2 and +3, they all have banked memory up to 128K, so I'll put that in here so I can emulate those machines as well. And then there's some stuff relating to the operation of the Z80 itself, and if I scroll down a bit further, so settings, various flags. So I've tried to set the flags in as efficient way as possible. So these ones here are actual calls, but on the other ones I've managed to avoid making calls to functions, and they're just very simple one-liners in the actual operation of the opcode, and that keeps things fast. By calling out to these, it's a bit of a slower process to actually make the call, but because these perform more operations, in order to keep the code simple and readable, I've preferred to do that for these particular flags. And then I've got the execute, which is just that what I showed you in the source code, the long list of opcodes, and it just goes around a loop in there, selecting which one to operate, increment in the memory or decrement in the memory depending on how things are going, and then doing the same operation on the next one. It just goes around that loop continuously, and then all this stuff below that is just debug code. So debug console. So I've put a debug console in there so I can step through machine operations, and because those comments that you saw in the Z80 source code where I've got the opcode names, I can actually produce disassembly when I'm going through the actual process of going through this debug console and stepping through the code. I could put breakpoints in and things like that. So again, this stuff in the debug region here isn't compiled into the actual release code. It's just if I compile a debug version of the code. Now I get to the emulation of the actual computer itself, and I'll go through the header file again because I haven't been through in the previous two. I don't think I went through the header files of the ZX80 and the ZX81. There's not much in here. It's just some simple stuff, like here I'm defining the default background for when it boots up, but the Spectrum soon changes the colours itself, so it's not so relevant to this. In the previous emulations, like the ZX80, I made it a green screen with black ink on, and the ZX81 I made a white screen with black ink on, so that when I'm running the two emulators, I can tell the two machines apart just by looking at the actual display. And so in here I've set up some actual attributes that are relevant to the actual ZX Spectrum itself. and then to do with this is all to do with what information you get in an I/O call, which we'll go through the source code of that in just a second. I'm going to just go over the relevant stuff in here. There's not much in here. So here's the keyboard layout. So unshifted keys and shifted keys. So I'm mapping these keys off of my keyboard onto the keyboard matrix, so that when I get an input call from the CPU, I can look up what my key press was to what the actual matrix value should be, and I return that matrix value. So this is actually the same for all the ZX81, ZX80 and the Sinclair Spectrum. I haven't changed this. So it uses the same matrix basically for all three of those machines. So you see the evolution of the actual hardware itself. There's parts of the hardware which are exactly the same in all three of the machines, even though things change behind the scenes a bit. But that's why earlier when I was saying that the machines are virtually the same for the emulation, even though the Spectrum's color computer and stuff is, you know, when we see the source code, you'll see exactly what I mean. So here I've got the color lookup table, so I can change the actual default system colors, but I've put the ones in which are relevant to the actual Spectrum. And you'll see this gives you a clue as to how simple it is. There's three actual functions to actually do the emulation. There's the main function itself to actually start the program and get it running, and then there's the keyboard callback. So there's only one I/O port that I use on here, so in that respect it's simpler than the ZX80 and ZX81, because the ZX80 and ZX81, well, the ZX80 had 2 ports, the ZX81 had 3 ports, because then it needed a non-maskable interrupt I/O port as well, whereas the Spectrum, then you reduce that down to just 1 port that it uses. And then I've got the clock callback as well, so that I get callback on every clock cycle, so I can decide what the machine needs to do on each clock cycle. So this is the actual machine source code itself, and I'll go through it, and it shouldn't take long to go through. So I've got some shared variables from the Z80 CPU. Now the reason I'm doing this is because for efficiency reasons, to keep the CPU speed up. So normally you might access these with accessor function calls. But I'm actually sharing the variables. It's considered not good programming practice, but then again, if you want the actual performance, then you know you sacrifice one thing for another. And as I'm going to hopefully eventually run this on a microcontroller, it might need all the CPU power it can get in order to run smoothly, depending on how the microcontroller actually how powerful that is. So at the top, like I said on the previous, if you watch the previous videos for Z80 and Z81, in the top these are just lookup values, which are actually on the Spectrum. I haven't really filled these in yet, because this is to help me debugging. As I step through the code, it can actually tell me from these comments on each line of the assembly code what the Spectrum's actually doing. From when I work something out, I put it into here, and then this then comes up automatically in the assembly listing. So I've put the system variables for the Spectrum in, which are here, so that when I'm stepping through code, it automatically puts the comments for the actual system variables. But I haven't looked at any of I haven't put the error codes in. Actually, that's something I should do, is put the error codes into here. If you look at the previous videos for Z80 and 81, I put the error codes into there. And then this is the character set for the Spectrum. So it's defined in the same way as I've defined it in the ZX80 and 81. But like I say, this one is ASCII, whereas the ZX80 and 81, they had their own custom sets. ASCII is only below 80 hex, so this stuff above 80 hex, this is custom for the Spectrum keywords. I think in the ZX80 some of the actual keywords were down in this lower part of the character set itself as well. So the main function itself, so which gets things initialized and running, it opens up a window to display the Spectrum emulator in. It does an audio initialization, so the audio stuff I've done really needs a bit more work on. It's just like a rough way of doing a beeping thing. I've not done much audio stuff in Linux before, so there's still a work in progress. And then it initializes the Z80, and then it loads the ROM into memory and tells it to write protect that ROM area so that nothing can write over it. Now on the preview on the ZX80 and 81, you would have seen here also mirror in memory. So the ZX80 and 81 mirror, I think it's 4000 hex to C000 hex. I think it was that address range, because it mirrors stuff so that the hardware can actually update the display from the mirrored memory and high memory. But you don't need to do that in the Spectrum. So the Spectrum uses the ULA, the custom chip inside the Spectrum, to actually use direct memory access to write stuff directly from the memory onto the display. So the CPU has nothing to do with updating of the actual display itself. The CPU, or the actual ZX8 Spectrum, writes into memory map what it wants to display on the display, and then the ULA chip takes that memory and sends it up to the display. So you don't need to do any memory mapping in here. So again, like I was saying with these ports, there's only a keyboard port, so there's fewer ports on the Spectrum, and there's also no memory mapping on the Spectrum, or the 48K Spectrum. We'll talk about the 128K Spectrum when it has to handle 128K in a different video when it does memory banking. And then there's the clock callback as well, and then it starts the execution of the Spectrum ROM, and then after it's finished it closes the window and closes the audio as well. So if you look at the previous videos, that's virtually the same for the other two machines. The keyboard callback, so it handles the sound going through the little beeper device on the computer, which the other two don't do, but that's only a small piece of code in here. And then what it handles is saving and loading stuff. So saving and loading stuff is done using ports again in the same way, but the actual format of the saving and loading beeps and stuff is done differently. Now I haven't actually put that code in here at the minute, like you saw in the demonstration of the games, I'm saving and loading snapshots, which is a way of just bringing stuff directly into memory rather than going through the cassette interface, which is here. And so I need to update this code so it does loading and saving to cassette, because I'd like to be able to do that from a microcontroller. As you can see there, I copied and pasted this from the Z81 code. So that's going to be very similar, just handling beeps in a different way. Then further down here, so then it does keyboard access, and this code, I haven't changed this code, so this is the same code for the ZX80, ZX81 and the Spectrum. It handles the keyboard in exactly the same way on the same port. I'm pretty sure, yeah, I think pretty sure it's the same port as well. So there's the evolution of the hardware. It's it's doing the same stuff. And this, so that support no longer exists here. So the actual saving occurs also on the other port now. So that's why this is commented out at the minute, because I've got to move this onto the other port and do saving and loading on the same port. And then this is the clock callback, and this does very similar stuff to the Z80 and 81. So the Z81 did a non-maskable interrupt on here, which this doesn't, because it doesn't need to do it for the display, and the Z80 didn't do it for the display. I've added this to detect when the snapshot has been requested to be loaded, and it loads it into memory at this point. These are cassette load and save memory captures sort of thing, where I trigger on someone typing a load command or a save command. Again, because I haven't implemented that code, that's commented out here for now. And then there's just one thing left, and that's to do the update of the display. And if you look in the other emulators, it's actually a very similar amount of code. It does it differently though, because on the ZX80 and 81, it does a hardware interrupting system where when an interrupt occurs, and it then looks up stuff in memory depending on what memory has been accessed, and then it displays a byte of data on the screen depending on how it looks it up. Well, that doesn't happen like that here, but the process is very similar. It goes for a loop of memory locations here to here, and in those memory locations are the actual data itself, and there are ways of decoding the memory locations to decide what data needs to be displayed, and then it looks up attributes as well from a different memory location, which is related to what you're displaying. It decides on what paper and ink color needs to be done, and if it's flashing, then it inverts the paper and ink color to the other way around, and it flashes. I've taken the as a clock frequency at a certain number of count on the clock, it flashes at that rate. So the ULA on the system would handle the flashing of the display as well. And then it's just literally a plot in X and Y, and you see in, I'm not sure if, I think it's in both the others, or at least the Z80 one, I've changed it from being calling a plot of 8 points in a loop to just sending the byte to the plotting routine, because it's a much more efficient just to do one call to a routine rather than 8 calls to the routine to do eight bits when the data's the same that you're going to be sending there anyway. So you might as well just do a function to do the 8 bits. And then it says display refresh, which means draw it onto the actual Linux window, and that's all it needs to do. So there's not much code to doing the emulation of any of these machines. And when you actually, if you go back and look at the other videos, the actual emulation of the color spectrum with its beeper is very similar to the emulation of the ZX80, and you can pick up on the similarities in the hardware and the evolution of the hardware. And it's quite an amazing machine. All of them are quite amazing machines.